Hello and welcome to another episode of TWiML Talk, the podcast where I interview interesting people doing interesting things in machine learning and artificial intelligence. I'm your host, Sam Charrington. Today we're joined by Aydogan Ozcan, Professor of Electrical and Computer Engineering at UCLA, where his research group focuses on photonics and its applications to nano and biotechnology. In our conversation, we explore his group's research into the intersection of deep learning and optics, holography, and computational imaging. We specifically look at a really interesting project to create all-optical neural networks, which work based on diffraction, where the printed pixels of the network are analogous to neurons. We also explore some of the practical applications for their research and other areas of interest for their group. And now, on to the show. All right, everyone. I am on the line with Aydogan Ozcan. Aydogan is a professor in the Electrical and Computer Engineering Department at UCLA. Aydogan, welcome to This Week in Machine Learning and AI.
Well, thanks for having me, Sam.
So you are currently working at the intersection point between optics and deep learning, and I'm really interested in jumping into this and learning more about the work that's coming out of your research group. But before we do, tell us a little bit about your background and how you started working with deep learning.
Sure. Yes, I work in optics, applications of optics, specifically computational imaging and sensing techniques, where we're creating new types of imaging systems, new types of microscopes and sensors, with heavily focusing on applications in biomedical space. For example, pathology, creating new types of microscopes in pathology. At the same time, different types of sensors for telemedicine, mobile health-related applications. And more recently, we're interested in environmental monitoring, looking into water and air quality. And there's a huge opportunity ahead of us at the intersection of optics and machine learning that we've been exploiting for the last several years. It first started with essentially using machine learning to look at the images that we reconstruct and finding specific targets of interest. Let's say you're looking at certain parasites in drinking water, and you create a mobile microscope and create images of particles inside your observation volume, chamber, disposable cartridge. And then, of course, you need some sort of a machine learning tool to look at what's captured there and specifically label, let's say, certain parasites of interest. So it starts from that direction of annotating images and looking for specific signatures that you're after. But more and more recently, we're realizing the power of spatial deep learning to design instruments, to design sensors. From image labeling, image classification, we're moving toward data-driven designs for optical instrumentation, for optical sensors. In a sense, I've spent easily the last 10 years creating new types of computational reconstruction methods for different kinds of microscopes, holographic microscopes, for example. And in the last few years, we're realizing that we're moving from physics-driven solutions to data-driven solutions. How data and the framework around deep learning, holistically, they're helping us to essentially better reconstruct images, especially for holography. We've seen some great examples of that, where without any iterations, training purely a neural net based on input-output labels, you can actually reconstruct holograms much better than traditional methods of solving an inverse problem. And that's very, very exciting for actually optics community at large as a whole.
What does it mean to reconstruct a hologram? What specifically are we trying to do there?
So one class of mobile microscopes that we've created is actually using diffraction of light. In fact, holographic shadows of specimen to reconstruct images. So in this line of work, you're taking, for example, a CMOS imager, like a CCD or a CMOS imager, the same thing that you have at the back of your cell phone, and place specimen right in front of it without any lenses, where the specimen can be, let's say, a pathology sample or a smear. and you shine light through it. And you capture with that simple configuration, with a simple 510 megapixel imager, the diffraction hologram of a specimen. So that contains all the three-dimensional information of the specimen, but it needs to be reconstructed because it doesn't immediately give you the microscale information of the sample. It gives you a hologram, which is light interference. The light scattered by the object interferes with the background light, giving you some fringes and a hologram.
Mm-hmm.
And it needs to be reconstructed. So physics is great at providing us tools to do this reconstruction. But nowadays, one alternative method that we've been exploring and being very successful at is to use actually holograms as inputs to a neural net that is being trained with reconstructions, gold standard labels coming from physical reconstruction methods, which are, relatively speaking, cumbersome in the sense that they're typically using some iterations to clean up the image and give you something that, with reasonable resolution, shows you what's going on in your sample. Now we're seeing that through data, you can actually teach a neural net to reconstruct a hologram from those interference patterns, from those fringes, to go back to the sample plane, sample volume, to give you all these signatures of the samples. Better than before in the sense that this reconstruction is now extremely fast, and it can also provide some better rejection of some of these interference artifacts that are common to holography. This is just one example where data-driven approaches are providing alternatives to intuition that driven by physics to do a reconstruction.
Mm-hmm. And so in this case, is your ground truth an image that is imaged like traditionally, like with a lens in front of the same type of CCD, and then you take an image of the same subject without the lens, just using the diffractive patterns, and that's how you produce your labels, or is it more involved than that?
You can definitely take that approach and use standard microscopes to create labels. A better approach is actually to use traditional physical reconstruction methods that take maybe a bunch of holograms to reconstruct the sample's information. Different than a traditional lens-based bright field microscope, holography has two different channels of information. One of them relates to the amplitude of the sample, amplitude of how the light is scattered, and the other one is the phase information of the sample. And that's where holography is very powerful as a coherent imaging modality. And that's why a better approach to use as gold standard ground truth images is actually coming from traditional holographic reconstruction solutions. They provide essentially the physics-enabled ground truth. And after we've done that, we see some very interesting results where it solves the inverse problem in a different path, but very robust in terms of what you need to see, what you need to kind of reconstruct at the micro scale for both of these channels that I mentioned, phase and amplitude. The phase channel is extremely important, especially for transparent samples like jellyfish, for example, like the thin samples that do not scatter light as much.
And is the reconstruction that you're targeting, is it a visual reconstruction that you might get if you had a traditional microscope, or is it something different that better captures the two types of information that you have access to with holographic images?
It bears the advantages of holography in the sense that it can look at these two different information channels that I mentioned, amplitude and phase, and at the same time over a larger volume. One advantage of holography is it can see objects at different depths without a physical focusing mechanism. You can time reverse the optical field and go to different depths within your sample. And that gives an advantage to a holographic reconstruction. And it essentially gives you microscopic features at different planes of your sample. And that's what the network output gives you. And we've shown that actually, if you train the neural net with different holograms acquired at different sample to sensor distances, you can extend the depth of field. In other words, the neural net can be taught to not only holographically reconstruct objects, but autofocus them as well, which has been very interesting. Imagine, for example, as a volume of a sample, which contains several different objects, cells scattered, for example, in a volume. You can actually bring them all into focus within the reconstruction. And that's something that we've recently shown as a holographic reconstruction, doing both standard hologram to image transformation that physics has been very powerfully doing for decades, but at the same time merging it with autofocusing so that different parts of the sample come into focus digitally at the output of the network.
And what do these networks tend to look like? Are they convolutional neural nets with kind of traditional architectures, or are you doing very domain-specific things in the various layers of the network?
Well, these are powered by convolutional neural nets, and we're taking essentially standard architectures, but of course fine-tuning them without making them unnecessarily complicated. At the same time, because it's a microscopic imaging modality, we're also fine-tuning some of the parameters in this space to make it learn this transformation across different spatial features. Mm-hmm. So that it can actually reconstruct larger features at the same time, subcellular features, for example, if you're looking into a cell.
And when you're building these networks that essentially map from this kind of raw data from the imager to the result of something that's trained on the physics-based reconstructions, is there anything about the networks that you've seen produced and their function that suggests that the network is learning structure that's analogous to the rules of physics that that govern the system, or is it taking shortcuts that don't necessarily relate to the physical representation?
Yeah, fantastic question. So it learns whatever you teach it to do, and it rejects anything else, even though that something is physical. I'll give you an example. We've taught a neural net to do reconstructions of holograms, but these holograms were planar objects. Like, we were interested in tissues used in pathology, right? There are thin sections of tissue, and our goal was to reconstruct those tissue sections from their holograms. This was a plane-to-plane transformation in a sense that the sample is planar, its hologram is planar, and we were taking the raw holograms and transforming them back to how the sample should look like in its phase and amplitude. And the network was very successful, learning kind of like, without understanding physics, learning the physical principles of this transformation. However, it's rejecting anything else. For example, in our experiments, we usually have some dust particles that are seated somewhere in our optical path, above or below the sample, but not on the sample plane. These dust particles are unavoidable, especially if you're not having a vacuum type of environment. So in a physical reconstruction, those dust particles appear as some sort of artifact in the image. And we understand that that's a physical solution. That's a physical particle creating some sort of an interference pattern superimposed on the image of the sample, right? It's not part of the sample, it's somewhere else, but it's a physical particle. The network rejects that, although it appears in the physical reconstruction. The reason is the network thinks it's an artifact of holography. It doesn't seem like it's in focus. It's an out of focus, dust particle or artifact related to that. And actually, it's rejecting those kinds of physical, but outside the solution domain type of pixels. And that's very powerful in the sense that you see in the physical reconstruction some artifacts that must be there, but they're actually attacked by the network. Similar things that you can mention for particles or objects at different depths. Physics give you a certain solution, and the network sometimes violates that, but if only it is part of what you've trained it for.
So you said that the physical reconstructions do contain these artifacts from the dust particles, and these are your ground truth. How then is the network learning to reject them?
Well, they're rare, right? So that's the good thing. The physical reconstruct that the dust particles are obviously happening rarely. Like over a large field of view, maybe you have a few places, and by and large, everything else is plane to plane. That's why it generalizes to that transformation and attacks anything of that nature.
You're creating these new types of reconstruction methods. How else are you applying deep learning?
Well, a recent work that we've done on optics deep learning intersection is actually creation of an optical network, optical neural net that's based on diffraction. So it's not a traditional deep neural net in the sense of standard convolutional neural nets with nonlinearities like rectified linear units, etc., that you find in electronic neural nets. This is actually an analogous to that. It's an optical analog of it, where imagine the input is an object where you shine light, and behind the input there is an optical construct. It's a passive system, meaning you design this optical hardware using a computer, using deep learning principles. And once you optimize it, you fabricate it using a 3D printer if your wavelength is of interest to that, or using lithography. You fabricate features to craft essentially a volume. And that volume, as light is penetrating from the input plane into the diffractive layers, is solving essentially a problem, let's say a classification problem. And that volume is composed of different layers, where every layer is composed of several pixels, thousands of pixels. And these pixels are representing what we call as neurons. The transmittance, phase and amplitude of the transmittance of each neuron is a trainable, learnable parameter. And at the end of the network, there's a light pattern, and that light pattern is the output of your network that you're trying to solve a problem. Let's look at, for example, a classification problem. A simple one, let's look at classification of handwritten digits. If I input to this network zeros, like handwritten 0 digits, the light that is transmitted from that object is diffracting through these different layers that are all optimized to guide the light to a certain detector at the output plane that is assigned to 0. If I bring a new 0 handwritten, if it's correctly built, it's going to actually channel most of the photons at the output to the correct detector, saying that it's all optically inferring that it's a 0. Same idea applies for other classes, and it's all optically essentially using diffraction, solving this problem that you asked the network to solve.
This is really fascinating to think of, that you can implement a deep neural net all in optics. You mentioned that the pixels are analogous to neurons in a traditional deep neural network, and that the parameters can be learned. Are you learning those parameters, offline, so to speak, meaning before you're printing this network, or is there somehow, these networks are not, they're mutable post printing?
Great question. So yes, let's think first an entirely passive system where it's fabricated and fixed. Before that fabrication process, you use a computer to finalize through deep learning, through backpropagation, error backpropagation, you finalize the transmittance values of each one of these neurons. And then you fabricate it, so it's essentially fixed. But you can also create a hybrid system where some of these layers are composed of dynamic light modulators, like spatial light modulators, where you can actually change them and make them as part of a learning scheme, or kind of like mend the network's function. But in the implementation that we had experimentally, these were trained using a computer in TensorFlow, and then fabricated and then all optically tested with light as input, passing through some input. One thing that's very important here is that this framework it has two branches to it. One, you can create something with this kind of layer-to-layer design using linear materials, linear optical materials, meaning that they are essentially not including any nonlinearities. As a result, if you use no nonlinearity in your diffractive layers, this becomes a linear classifier, meaning that you can have all these different layers, free space propagation of light, and a diffractive layer, some more free space diffraction, some more layer coming after it, and repeating the same process. All of this can be mathematically squeezed into a single matrix operation. But even using these linear materials, the network has depth to it. And that's where the diffractive deep network, optical network analogy comes from. The depth of the network is because of this. You cannot take a single layer between the input and output planes and generalize to any function that multiple diffractive layers collectively can produce. In fact, we've shown that as you add more layers to this system, one after another, all trainable, your network gets better in its classification, and its power efficiency, its output contrast per detector, per class, improves as the number of layers increases. So that's one aspect that I would like to emphasize. And the other aspect is...
Before you move on, just to make sure I understand this, are you saying that adding additional layers inherently introduces nonlinearity, or that you're using nonlinear or materials with nonlinear reflective and refractive characteristics to introduce the nonlinearity?
So certainly we can use nonlinear materials as part of the diffractive layers to introduce nonlinearity in the system. And then it becomes a more sophisticated tool in terms of how different kinds of functions it can generalize. So you can include nonlinearities like nonlinear materials, crystals, polymers, semiconductors as you fabricate these things as part of the network to introduce nonlinearity. But what I was referring to is the fact that even though you don't have any nonlinear material in this system, there is depth to it in the sense that multiple layers perform or have more degrees of freedom to perform a more general function better than a single diffractive layer. And that's where, even with the linearity of the material, there is depth, deepness of the network in its performance.
You've got this essentially a classifier that you've printed. Just to make this very concrete, what type of scale are we talking about physically?
Great question. So we tested these experimentally using terahertz wavelengths. The wavelength of which in air was about 0.75 millimeters. So it's a big wavelength. It's terahertz. That's why we were able to use, luckily, a standard 3D printer, which is transparent at those wavelengths, and we could put many layers, like 5 layers, one after another, forming a diffractive optical network made out of literally plastic coming from a 3D printer. And the size of this network was on the order of 8 to 9 centimeters. Obviously, at divisible wavelength, at shorter wavelengths, what you're looking at is maybe a half a centimeter by half a centimeter type of a network in terms of width, which would be sufficient in terms of number of neurons, etc., that you can fabricate there with lithography.
So 8 to 9 centimeters sounds very large relative to what I had envisioned for this.
Because the wavelength is very large. So,
right.
So the wavelength, as I said, is about 0.7, 0.8 millimeters.
Mm-hmm.
But when that's almost about 1,000 or 800 microns, right? So if you go to visible wavelengths, submicron wavelengths, you're looking at a drastic reduction in the size. And that's why a few millimeters by a few millimeters would be the size of this kind of a network. working in visible wavelength, let's say in green wavelength, like half a micron wavelength. So that's why everything will be scalable to the wavelength.
Sure. In this terahertz wavelength that you fabricated, the 8 to 9 centimeters, is that 8 to 9 centimeters square for the plane that the light initially hits? And then is there a separate depth for this, or is it 8 to 9? What dimension does that 8 to 9 millimeters refer to?
Great. The 8 to 9 centimeters.
Centimeters, right. Sorry.
is the width, and the depth of this system is actually layer-to-layer spacing is only 3 centimeters. So essentially, you're looking at maybe a cube of 8 centimeter by maybe about 15 centimeters in total depth. The spacing between the layers being 3 centimeter. We also had another network which was much more compact with a 4 millimeter gap. But you should all convert these to wavelengths, because that's what is more relevant to discuss, because here we use a specific wavelength. In terms of wavelength, we're looking at layer-to-layer spacing of less than 50 wavelengths. So if your wavelength is, let's say, a micron, you're talking about 50 micron at most layer-to-layer spacing, sub 50 micron. In terms of the width, we're talking about maybe 100 wavelengths in terms of width and height of the network. So in that regard, these are really very compact networks that will scale down with wavelength. Obviously, in this example, we've used off-the-shelf 3D printers, and that's why terahertz was used to show the fidelity of this thing with relatively very inexpensive fabrication methods. It costs us only a few dollars to print one of these things with 3D printers. Lithography would be more expensive, but with economies of scale, obviously, the fabrication of something like this using glass and using photolithography would be no different than fabricating, for example, your CMOS imager at the back of your cell phone. In that regard, it will be also pennies at large scale fabrication.
And in terms of visualizing what the layers might look like, should we or could we think of them kind of as like Fresnel lenses, or maybe more digital patterns like QR codes? Or is there a way that you could articulate what these things might look like if we were looking at a layer individually?
Each layer would look like a speckle pattern to you. It wouldn't mean much. But as you come toward the output layer, you will see emergence of some patterns depending on where you put your detectors. So essentially, it's a gradual shaping of statistical wavefronts coming from different objects that you've learned to classify. So it's very difficult to exactly understand how they work together. Because there are multiple layers, and your signal is essentially a stochastic signal in the sense that it can come in different forms. But what you can see from each layer is that there's a phase pattern, and it's slowly emerging at the output to shape itself as if it's facing a bunch of detectors that each of which is assigned to a class. If you have 10 classes, then you're looking at 10 detectors at the output, so that the inference is all optical except the final detection part per detector. So obviously, you can have more detectors too beyond the class. In fact, in our recent work, as a follow-up on this, we've shown the merge of these diffractive optical layers forming the all-optical network with electronic neural nets. So it formed kind of like a hybrid system where the front end was all optical and the back end was standard neural nets with the standard nonlinearities, etc. So that obviously has some very interesting and appealing features. And one thing that we've shown is that the input pixels to the electronic neural net can be compressed by the all optical network if they're both optimized at the same time. the optical neural net and the electronic neural net, if they are optimized jointly, we see some very interesting advantages. But this is something that's unpublished. We just put it into archives. We're seeing some very interesting hybrid systems that can emerge from the same diffractive neural net concept.
And how is that physically implemented, this mixed mode system?
So this was an analysis, but in an experiment, imagine you take an optoelectronic sensor, let's say 100 pixel by 100 pixel, or a few hundred pixel by a few hundred pixel type of design. In front of it, as if you're putting a lens, you're going to be putting a bunch of diffractive layers.
Right. Okay.
That have been optimized for a certain inference task. Assuming that there is a very simple neural net that is running beyond the CMOS. And that's the CMOS or the CCD, the low pixel count CCD or CMOS imager is kind of like the layer between the optics and the electronic neural net.
And are you using it as an electronic or a dynamic detector? Is that its role, or are you also implementing layers beyond that in the analysis that you did?
We've shown it works as a classifier, just like the all-optical network, but a better classifier. And it also takes a very primitive neural net that the inference performance, like not very deep, not a lot of trainable parameters, very low power requirement type of a neural net. You can take something like that and make it work very good. So in a sense, it will be very useful, especially for low power and mobile systems that need to frequently, with a very high frame rate, look at some scene or some data. That's where you don't have the luxury of working with, very sophisticated neural nets for power reasons, for frame rate reasons, etc. That's where optics can help because of its speed and its front end, making the rest after the digitization step to be compact in terms of number of pixels, in terms of frame rate, being fast, and also the depth of the electronic neural net or the complexity of the electronic neural net becoming kind of much less advanced compared to a purely electronic neural net.
Your experiments were based on an MNIST-style database, handwritten digits. Do you have a sense for the way the physical characteristics of the layers change with the complexity of the underlying data set, the input data?
We've also tried another data set which is known to be more complicated. It's called the fashion MNIST. So we had 10 different classes of fashion products like sneakers, bags, T-shirts, trousers, etc., etc. Mm-hmm. It's not as challenging as CFAR 10, for example, but it's more complicated than fashion MNIST. So we've also tried that and shown that another network trained for that data set, 3D printed and tested experimentally, works nicely to match our predictions or numerical analysis. In terms of complexity, hard for us to understand what changed from MNIST layers to the fashion MNIST layers into, as I look at them in front of me, they look similar to me, but of course the detail, like all the details are hidden there in terms of the face profiles of each layer. So it's very difficult to obviously understand.
Sure, but there wasn't anything obvious like you needed to go wider or deeper to achieve reasonable performance.
No, of course, there's a huge parameter space that we need to optimize here, and maybe there is more room to optimize to improve the inference performance for more complicated data sets. Mm-hmm. So it's still research ongoing in that regard. But what we've shown is that the same 5 layers with the same number of learnable, trainable parameters worked. Of course, lower accuracy compared to MNIST because fashion is more difficult.
Mm-hmm.
But essentially, it's the same framework that nicely generalizes for another task. But how well you can push it further, it's still a research question. In fact, in one of our recent work, we have improved. For example, the paper the science paper reports something like about 92% for MNIST. We pushed it to now 98% without using any nonlinear optical materials, with some changes in the way that we optimize the neural net. Optical neural net. So essentially, we've already optimized and improved some of the parameters that we've been using in designing this diffractive layer set to push it by a good margin from, as I said, for MNIST, for example, from about 92% with 5 layers. Now we're approaching 98% with also 5 layers, same number of trainable parameters. So it's a lot of different things that you can do to improve the performance of something like this. And one unique aspect of diffractive layers is it's passive, right? I mean, once you fabricate it, it doesn't consume any power except the illumination power and maybe the detectors that you have at the output plane. But everything else in between is just material. It's just you fabricate it and it stays. It's good. It doesn't consume any power, but it's bad. It's static. Right. If your data changes, you need to reprint it. But one thing that we've shown is actually you can take a neural net with optical neural net with several layers and peel off some layers and add new layers trainable with respect to the rest of the static ones, and kind of mend and improve the performance of the entire system. So it's in that sense, it's like a Lego piece.
Kind of like fine tuning applied to a physical network.
Right. Exactly. So you take different layers, you take out some of them, or you patch additional layers onto an existing one. That's one way of bringing some reconfigurability to the system. Another way of bringing reconfigurability to the system is replacing some of these layers with dynamic electro-optic modulators. Right. So rather than printing and having the code as part of glass permanently, you have a layer that you can actually change the pixels. Spatial light modulator type of systems. Of course, you can create a hybrid system where some layers are static, some layers are dynamic, and create some sort of a trade-off between complexity and reconfigurability of diffractive layers.
This is really fascinating. How do you see this playing out? Do you see practical applications for this, over some arbitrary time frame, and what might those be? Or is this kind of a research direction that's driving you on a broader path that that you're not necessarily trying to see this used practically?
First of all, we're enjoying playing with it. It's a toy, and it's making us happy. So.
It sounds really fun. I can definitely see that part of it.
Yeah, it's certainly a good toy that keeps you awake. It's like a good puzzle, right? I mean, so many things that you can do with it and try different things. And it's just at its infancy. So it's our baby and we're trying to, play with it and be happy. But at the same time, there are so many interesting applications that we foresee. I believe for defense and security, it has tremendous applications, especially at longer wavelengths, infrared wavelengths, mid-infrared wavelengths, where some of these thermal cameras or other types of focal plane arrays. I think those will benefit tremendously from an optical front end, because a megapixel at those wavelengths, a megapixel imager at those wavelengths is very expensive, and not every country has the know-how to fabricate something like that. So I think for defense, the applications are enormous. Overall, I'm very excited about one direction that I've been constantly thinking, and that is to create low-power and mobile hybrid systems that are powered at their front end with some all-optical machine learning front end. At the backside, an inexpensive CMOS or CCD, followed by a very modest low-power neural net implementation. It can go very low power this way. It can be extremely fast this way. Frame rates can be very high. And at the same time, we're talking about very modest form factor. So that obviously has, to me, some very interesting security applications at different parts of the electromagnetic spectrum. And I can obviously, because of my background, think enormous amount of biomedical problems that one can tackle with this kind of a front end integrated with optoelectronic sensors and electronic neural nets. That's one area. And the other area that I'm very excited about is actually nonlinear materials, metamaterials, plasmonics, exotic material systems. As we discussed this in our paper that we published in Science, the nonlinearity aspect of material science, optical nonlinearities in material science, I think opens up a huge plethora of opportunities for enhancing the function of something like this. And that's where I think some of these metamaterial-based exotic structures, plane by plane by plane, following each other, would really generalize some very sophisticated functions, maybe coming close to electronic neural nets with favorite choices of nonlinearities. We'll see how it goes, but this is another area where I'm very excited about.
Well, Aydogan, thanks so much for taking the time to walk us through what you're up to. This is really fascinating, and it sounds very fun. So your group must have a good time playing with this stuff.
Thank you. Really, yeah, we're enjoying ourselves. We're enjoying the time, yeah. Thank you so much for having me.
All right, everyone, that's our show for today. For more information on Aydogan or any of the topics covered in this show, visit twimlai.com/talk/237. As always, thanks so much for listening, and catch you next time.